Okay, in this next part of Concept 41, we'll be talking about transformations of exponential functions. The base form is f of x is equal to a times b to the x minus h plus k. Some of these values here should seem familiar because we've seen them before when we were talking transformations of quadratics, absolute value functions, and our root functions, and they work the same way here. Okay, h here is our horizontal shift. If it's positive, then that means you plugged in a negative, which means you shift left. If it's negative, that means you plugged in a positive, which means you shift right. If you guys recall, it was like considering the opposite sign. K is the vertical shift, and then this one, if it's positive, it shifts up, and then if it's negative, it shifts down. If a, the value in front, is negative, the function is a reflection across the x-axis. If the absolute value of a, the value in the front here, is greater than 1, then it represents a vertical stretch. And again, the way to think of this is for each values you plug in and you evaluate, if a is bigger than 1, then you get a bigger value, so it's a stretch. In other words, you get a bigger value there. If the absolute value of a is less than 1, for whatever you evaluate here, this is going to make it smaller, so it's a vertical compression. Okay. For our examples here, it says directions A, identify the parent function, and B, describe the transformations. So number 1 says f of x is equal to 3 to the x plus 5. So for part A, the parent function here would be f of x is equal to the base, which is 3, to the x. And then describe the transformation. So from my parent function here, I have plus 5, so then I go up 5 units. And that's it. For number 2, I have 2 times 1/4 to the x minus 1. So then my parent function here, just take the base, 1/4, to the x, not x minus 1. Okay, that's part of the transformation. So then B, part B, describe the transformation. Okay, we have a vertical stretch, because it's 2, it's bigger than 1, of 2, comma, and then it's negative 1, so I go to the right 1 unit. Number 3, I have a negative in the front. Okay, well, actually, hang on, before I do that, let's describe our parent function. F of x is equal to, again, just the base, 4/3, okay, to the x. Now the transformation here is reflected across the x-axis, and then you go to the left 2 units because it's plus 2, which means I plugged in negative, so left 2 units, and then I have plus 7, so up 7 units. Number 4, I have a half times 5 to the x minus 4 minus 2. Parent function here is the base, 5 to the x. My transformations are, I have a vertical compression this time because a half is less than 1. Compression of a half. I'm going to the right 4 because it's minus 4, so I plugged in a positive 4, so right 4 units, and then it's minus 2, so down 2 units. For this next part, we're going to apply what these transformations are now and be able to see what the graphs are. So the way we do this is we consider still the table xy for the parent function of the given function. So I have f of x is equal to 2 to the x plus 5. So then the parent function here is f of x is equal to 2 to the x. So I'm going to plug in my usual values here. When I plug in these values, okay, I'm going to get 0.25 or fourth, 0.5 or half, 1, 2, and 4. Now I have plus 5 here, which means that I plugged in a negative 5. So I have a horizontal shift of negative 5. My horizontal values across the x-axis. So this right here is what's gonna change. Okay, so with the transformation applied, f of x is 2 to the x plus 5. My table is not gonna look like this. Again, it's only a horizontal shift, so only my x values are affected. I plugged in a negative 5 here, so I'm going to shift all of these by negative 5. Negative 2 minus 5, I get negative 7. Negative 1 minus 5, I get negative 6. 0 minus 5 is negative 5. Negative 4, negative 3. Okay, my y does not change. And you can plug these in here, and if you do, you're still going to get the same value from here. So you'll see that your y values do not change. So I have 0.25, 0.5, 1, 2, and 4. So if we plot this table, okay, our actual given function here, negative 7, 0.25, so it's around right here. Negative 6 is 0.5 around here. Negative 5, 1 here. Negative 4, 2 is there. And then negative 3, 4 is here. We connect these dots. Okay, and we got this function here. So my domain, there's no restriction to what I can evaluate this function in. So my domain is all real numbers. Okay, for my range, you'll see that all the y values here, I get closer and closer and closer to 0. This horizontal line y is equal to 0, but I don't actually cross it. So my range is all values from greater than 0 all the way to infinity. So my range is all y is greater than 0, and I also know that my asymptote is y is equal to 0. As x approaches infinity, f of x is going to increase to infinity. As x goes towards negative infinity, f of x is going to get closer and closer and closer to my asymptote, but it's not going to cross. My asymptote is 0. For my y-intercept, we can't tell just by looking at our graph or our table where this graph is going to cross the y-axis, but we do know that on the y-axis x is 0, so you can just plug in 0 for your x, and then you find your y-intercept from there. So I get 2 to the 0 plus 5, which is 2 to the 5, and 2 to the 5 is 32. So then my y-intercept is at 0, 32. Next example, I have f of x is equal to 1/3 to the x minus 2. So same thing, I'm going to create my table x, y, and then my parent function here, f of x, is equal to 1/3 to the x. So plug in the usual values, negative 2, negative 1, 0, 1, and 2. And when you evaluate these x values in this function here, you're going to get 9, 3, 1, 0.3 repeating decimal, and 0.1 repeating decimal. There's no horizontal shift, but there is a downward shift. I'm going to go down 2 units. Okay, now that's the vertical shift, so then my X values do not change this time. Instead, only my Y values are going to change. So I have still the same X values, -2, -1, 0, 1, and 2, but I'm going to subtract 2 from each Y output here because it's a downward shift. So I have 9 minus 2 is 7, 3 minus 2 is 1, 1 minus 2 is -1, 0.3 minus 2 is -1.6 repeating decimal roughly, okay, and then 0.1 minus 2 is -1.8 repeating decimal. This is the table that I'm gonna plot now here to find what this graph looks like. So at x is equal to -2, I have 7, so 3, 6, 7, so about there. -1, I have 1 there, yeah, and then at 0, x0, I have -1 there. At x is equal to 1, I have 1.6, so approximately there. And then when x is equal to 2, I have -1.8, so almost touching or going or crossing y is equal to -2. So then you connect these dots here, and here's what this one is going to look like. You can keep plugging in x values greater than 2, and you'll see that you'll keep getting closer and closer and closer to -2, but you're never going to actually cross. So that right there is our asymptote. I'm going to draw this in red here. Okay. So in all the other examples, our asymptote has been y is equal to 0. In this case here, I have my asymptote as y is equal to -2. As x goes towards positive infinity, therefore f of x is going to keep getting closer and closer and closer to -2. And then my range, of course, is all y values from -2, so all y values greater than -2. There's no restriction to what I can plug in for my x values, so therefore my domain is all real numbers. As x goes towards the negative infinity side, f of x is going to keep going up or towards infinity. And finally, my y-intercept, I can tell from my table here, where x is equal to 0, I get -1. And that's this example here. Number 7, we have a new case here. So same process here. Let's create our table. -2, -1, 0, 1, 2. My parent function is f of x is equal to 3 to the x. My transform function is the same thing that's up there, 3 to the x plus 1. Now, when you evaluate this function for all these x values here, you're going to get 0.1 repeating decimal, 0.3 repeating decimal, 1, 3, and 9. Now let's look at our transformations here. My leading value here, is less than 1, so I have a vertical compression of a half, and then I'm going to shift up 1 unit. And the way you read the transformation is as opposed to going left to right. You start first with the compression and then you shift up. So, and notice that the transformations are only on my y values. There is no horizontal shift. So my x values stay the same: -2, -1, 0, 1, 2. First, I'm gonna compress all my y values by a half. Okay, so 0.1 becomes 0.05, 0.3 becomes 0.15, and it's a repeating decimal, so 1/6 if you round. 1 is 0.5, 3 is 1.5, and 9 is 4.5. That's all these values divided by 2, making them by half. Then, once you half all these values, okay, you add 1 to it. So 0.1 was 0.05 plus 1. I get 1.05. And then you could say that it's a repeating decimal. So we have 1.05 repeating. And then 0.3, we said it was about 0.16. Add 1, so you get 1.16 repeating decimal. Half of 1 was 0.5. Add 1, I get 1.5. Half of 3 is 1.5. Add 1, I get 2.5. And then half of 9 is 4.5. Add 1, and I get 5.5. Now I can plot these. So at -2, I have 1.05. So it's just, it's just above the y equal to 1 line there. At -1, it's slightly higher. And then at 0, it's 1.5. So right in the middle there. And then at x is equal to 1, I have 2.5 there. And then at 2, I have 5.5 there. Now you can draw my line here, and then the trick is pretty much where you see the y values approaching, that's where your asymptote is going to be. You can plug in values greater than smaller than -2, because as you can see, your y keeps getting smaller here, but as you go -3, -4, and so on, you're just going to be getting closer and closer to y is equal to 1. You can verify that in your calculators. So my asymptote here is y is equal to 1. As x goes towards -infinity, I know it's going to approach -1, and then my range is going to be all y values greater from that point. So y greater than -1. Sorry, this is not -1, it's +1. I apologize for that, it's +1. As x goes towards +infinity, f of x increases, so f of x goes towards infinity. There's no restrictions to what I can plug in here, so my domain is all real numbers. And then my y-intercept, I can see from my table, it's at 0, 1.5. I can also here just draw my asymptote so it's easier to see that that's the line. Oops, doesn't look too straight here. That's the line that this function is going to get closer and closer to, but not cross ever. Next example, number 8. I have f of x is equal to 3/2 to the x minus 4 minus 5. So my parent function here is f of x is 3 over 2 to the x, negative 2, negative 1, 0, 1, and 2. When I plug in my values here and I evaluate, I get 0.4, repeating decimal, 0.6, repeating decimal. When I plug in 0, I get 1. When I plug in 1, I get 1.5. And when I plug in 2, I get 2.25. I'm not going to write this function here because I'm running out of space. But when we apply the transformations here, okay, we're shifting 4 to the right, because I have negative 4, so I plugged in a positive. Okay, so I'm shifting 4 to the right, so I'm going to add 4 to all these values here. So my x's become 2, my x, negative 2 becomes 2, negative 1 becomes 3, 0 is 4, 1 is 5, and then 2 is 6. All I did was add 4 to all these values here. For my y's, I have 0.4 and all these here. I'm going to shift down 5 from each of these. Okay, so you can use your calculator to get the most accurate value. So 0.4 minus 5, I get negative 4.5, and it's a repeating decimal. 0.6 minus 5, I get negative 4.3, repeating decimal. 1 minus 5 is negative 4. 1.5 minus 5 is negative 3.5, and then 2.25 minus 5, I get negative 2.75. Now let's plug these in, graph these. 2, so add x is equal to 2 here, I get negative 4.5 here. Add x is equal to 3, I get 4.3, negative 4.3, so closer there. At 4, I get negative 4 there. And then at 5, I get negative 3.5. Let's see, 1, 2, 3, 4, 5. Let's see, I messed this one up already. So at 4, I had negative 4 right there. So disregard those two upper points there, I apologize. So at x is equal to 5, I get negative 3.5, and then finally 6, 2.75, so 2, and then 2.75, which should be around right there. So again, disregard these 2 points there, okay, and it's gonna look something like this. And then again, the trick is to just see what value your x values make this function approach. So then my asymptote here is negative 5. This function, and you can verify by plugging in those x values, you see that they never cross negative 5. So my asymptote is y is equal to negative 5. My y-intercept, this one might not work out so neatly, but if you plug in 0 for your x here, okay, and then see what does this function output, when you plug in that, you're gonna get negative 4.8 roughly. Okay, so this y-intercept there is negative 4.8. As x goes towards negative infinity, again, this function gets closer and closer and closer to my asymptote, so it's f of x approaches negative 5. As x goes towards positive infinity, this f of x is going to approach infinity. My domain, there's no restriction to what x I can plug in, so it's all real numbers. And then my range is from that asymptote going up, so it's all y's greater than negative 5. Finally, last example here, I have f of x is equal to negative 2 times 4 to the x minus 2. So have x and y, then -2, -1, 0, 1, 2. My parent function here is f of x is equal to 4 to the x. When you plug these in to the parent function, you're going to get 0.06, 0.25, 1, 4, and then 16. So what does this look like when we transform it? I have a -2 here up in the front, so it's a reflection across the x-axis, and then I also have a horizontal shift of 2 to the right side because I have a negative, so I plugged in a +2. So for all these x values here, I'm going to add 2 to each one, so I get 0, 1, 2, 3, and 4. Now for my y's, okay, I have a vertical stretch of the absolute value of the leading coefficient here, so it's 2. So for each of these here, I'm going to multiply by -2. Okay, so 0.6, it becomes -0.125. 0.25 times 2, I get -0.5. 2 times -2, I get 2 times 1, I get -2. 4 times -2, I get -8. And then 16 times -2, I get -32. So plugging or graphing these points here, at x is equal to 0, I get -1.25, so it's just below the origin there. At x is equal to 1, I have -0.5, so I have right there, right in the center. Then at x is equal to 2, I have -2 there. At 3, I have -8, so there. And then finally at 4, I have -32, so that one's not going to fit. So what this looks like is something like this. And this makes sense because I have a negative leading coefficient. Okay, that means that I have reflected across the x-axis. And my asymptote is y is equal to 0. So in other words, the x-axis here. So my asymptote is y is equal to 0. My range would be all values this time less than the that horizontal line there, y is equal to 0. So my range is all y values less than 0. There's no restriction to what I can plug in. All my x values are real values to this function, so domain is all real numbers. As x approaches infinity, f of x is going to go down, so it goes towards -infinity. As x approaches -infinity, it's going to keep getting closer and closer and closer to 0. And then my y-intercept to my table here, okay, it's at 0, -125. And that's it. This concludes concept 41.